absolutely cannot starve for even a moment, you can, they don't require insulin. So that's the whole point of insulin, is to make sure that if you need to cut off some parts of the body from the immediate insulin supply or immediate glucose supply, you can, to make sure that those vital areas that can't do without it never have to. Okay? All right, so we increase glucose uptake, and that of course leads to an increase in ATP production. And also an increase in protein synthesis. And that's not a direct effect, but it does happen. So that's the effect on all cells. All right, let me get down before I fall down. In the adipose tissue, we're going to see increased lipogenesis. Increased lipogenesis. Lipo, of course, meaning fat. Genesis meaning making. We're making new fat. Okay? Now, as we get into metabolism, you will see how this works. As you break down glucose, glucose is a 6-carbon sugar, or 6-carbon molecule. You eventually break it down into a series of 2-carbon molecules, or produce a series of 2-carbon molecules. Acetyl groups, essentially. You put them together into groups of 2. And then you will take that through and break those down and release carbon dioxide. Well, you can redirect those groups of 2 carbons into the process of lipogenesis. You just start stringing them together 2 at a time, and that builds up fatty acids. You can also take the 3-carbon portion of the glucose, after you split it in half basically, make that into a glycerol. Now you've got a fatty acid and glycerol. You can put them together, you can make a fat, right? Neutral fat molecule. Okay. Now you may recall the reason we do this is because that is an extremely space-efficient way to store energy. Right? There is no denser form of chemical energy than the carbon-carbon bond in the hydrocarbon, right? Which is, I don't know if that's, we didn't make that decision when we decided to run our civilization on it, but it seemed to make sense, right? Because there's no better way to get energy. Gasoline, fat, whatever it is, it's all essentially the same energy density. This is why batteries, as good, we have to get them as good as we can, because we can't afford to keep putting carbon dioxide in the atmosphere. But we gotta just realize that batteries will never equal the energy density of gasoline or diesel fuel. It's physically impossible. You just have to get them good enough to where they can kind of support what you have to do. And then hopefully the other advantages of an all-electric vehicle will overcome people's anxiety about range and charging time. Because imagine a car that doesn't need any maintenance, zero, other than maybe vacuuming and new tires, right? For 150,000 miles. That's what the recommended maintenance on a Tesla is. Put new tires on it whenever they wear out, but you don't have to have anything done to it for 150,000 miles. Now, of course, if I was an auto mechanic, I would not be happy about that.
So you have to buy a battery pack.
Huh?
You have to buy a battery.
Well, once that wears out, right? But for 150,000 miles, there's no oil change. Now, that, of course, the battery pack expense me. But they're talking about something like standardizing batteries to make them kind of in a removable tray, sort of like a battery pack that plugs into your drill. And having that like a public resource, sort of like propane bottles, you buy one bottle and then you just go trade it for a full one.
Interchangeable battery.
So you would go into a thing and then you would pull over this thing and this battery tray would come out and a fresh one would come in and off you'd go. You would kind of pay a rental fee for that. So it seems like a cool idea. But that's on the designing board right now. All right. So increased lipogenesis. Now the last thing is we have effects in the liver and the muscle. And that is increased glycogenolysis. Sorry. Had somebody complain about that word. I'm gonna lower this thing down. So give myself a little water. Okay. Now, glycogenolysis. What's glycogen? Remember? Crickets? Give my little cricket generator app. I used to have.
Accumulation of the polysaccharides,
It's a polysaccharide which is made of
monosaccharides.
Monosaccharides. Which one in particular? Glucose, right? So it's essentially strung together a bunch of glucose, right? And we're going to store this glucose in the liver and in the muscle. Now, the liver glucose is for the use of the entire body. The muscle glucose is only for use in the muscle, mainly fast twitch muscle, as we learned in AP1. Okay. Nevertheless, insulin has that effect. Of course, the accumulated effect here is to lower blood glucose. All right, now this is why we care when someone is hyperglycemic. Obviously, if they're a known diabetic and their blood sugar is too high too often, they accumulate that damage. That's why we have those, what is it, H1C, I think it's a hemoglobin H1. It could be a multiple things you can measure. It's a protein that accumulates sugar residues if blood sugar is kept too high for too long. And so they measure that in diabetic, and they're able to know how well the sugar's been regulated over the long term. Okay? It's like not flossing, and you go to the dentist and your gums are a little bit red at the edges, and the hygienist starts to floss and you're bleeding all over the place. You can't lie, right? You can't floss 2 or 3 days before the dentist and then them not know it. Try. But that is, that's why we monitor those things, right? So yeah, long term, it's obviously a problem. But short term, someone presents with hyperglycemia, right? And they're not a known diabetic. What's happening? Well, for what they are now, the insulin is either no longer working or they're not producing it. And so those cells are not able to take the glucose up, so they are starving. And what do? They start burning other sources of energy, notably fats and proteins, and this produces acidic byproducts called keto acids. And you end up with a condition called ketoacidosis, which, like other forms of acidosis, means your pH is too low, and that ultimately can result in death if it's not treated quickly. Sorry, so this is the kind of the immediate life-threatening problem. So that does take a while to develop. All right, so what about blood glucose falls too low? So we have hypoglycemia. And that, of course, is immediately life-threatening. Because if you have hypoglycemia, then not only are the tissues that normally depend on insulin, they don't have anything, but the ones that don't depend on insulin, the brain and the heart, they don't have any glucose either. Right? When diabetics get into trouble and either become very ill or even die from diabetic comas, it's not because their blood sugar went too high, it's because it went too low. They didn't eat enough, they took too much insulin, whatever that is. Okay? It went too low. And that, of course, can kill you rather quickly. All right, now this is detected also in the pancreatic islets. by the alpha cells. And they release the hormone glucagon. Now, glucagon has many fewer targets because what's it going to do? It's going to try to increase glucose availability, and there are only a few places you can get it. All right? Of course, the main place is in the liver. Also the muscles, but remember, the glucose in the muscles is going to be for the use of the muscles. There's a little chemical trick it does to keep it from leaving the muscle, so it can't actually be used by the general tissues of the body. Okay? And what's going to happen there is we're going to have an increase in glycogenolysis. Oops. I made a mistake over here. This should be glycogenesis. Please change that. We're making glycogen here. Down here, I'm breaking it down. Glycogenolysis. And of course, that releases the insulin, that coming from the liver to the whole body, that coming from the muscle is just for the muscle. Right? So that seems pretty straightforward. Been a few hours since you've eaten, blood glucose level starts to drop. So you release the glucagon, and all that glycogen you've been stored in your liver, you start to break it down and now release that glucose back in your bloodstream. Okay? There's another way to get glucose as well, but it requires some chemical magic. It requires some unique biochemistry. If there's any place where unique biochemistry happens in your body, it's in your liver. Your liver is your body's chemical plant. And one of the things that you can do in the liver is you can make new glucose. Gluconeogenesis. New, genesis, make new glucose. Obviously, you don't make it out of nothing. You make it out of other things. For example, you can make it out of fatty acids. You take the fatty acids, you take them down 2 carbons at a time, you string them together into a 6-carbon glucose. You can also make it out of certain amino acids. Okay, matter of fact, when we metabolize amino acids, we take the amine group off of them, and then we can use them for things like making glucose. This happens in the liver. What happens to that amine? In H2, we put another hydrogen on it, it becomes ammonia. And then we convert that to urea, and that's what we get rid of in our urine, right? One of the main jobs of the kidneys, the urinary system, is to get rid of nitrogenous wastes, which are left over from the metabolism of amino acids, which we metabolize so we can make them into glucose. Or divert them into fat. It's a little bit complicated, all right? So increasing gluconeogenesis. But there's also an effect on adipose tissue. And there we see an increase in lipolysis. And of course, that's going to feed into the gluconeogenesis. problem of all that, of course, now is to raise blood glucose. Questions on that one? Yes.
Are we gonna discuss how this relates to like, diabetics needing amputations and?
Well, I mean, we will later on more, but what happens is if you have consistent hyperglycemia, you don't either can't or you don't do a good job of regulating your blood sugar. You don't want to put blame on the patient there, but of course,
Yeah.
sometimes they do contribute to this problem by not staying on top of their blood glucose. Well, hopefully the newer technologies with the implanted monitors and so forth will make that less common. But if you have that elevated glucose for too long, then you get glycosylation of various proteins in your body, and this leads to progressive damage to nerves and blood vessels. And that leads to a neuropathy where you can't feel when you're injured, and so maybe you'll get an infection and not even know it. It also leads to the problem of blood vessels, leads to slow healing, and then eventually you get something like gangrene set in, and then you need an amputation. Right. It also leads to blindness, retinal neuropathy, and various other problems. Okay. Yeah, it's a huge health problem in the United States, and just getting worse. All right. Okay, so now let's talk about blood pressure. Now, blood pressure, of course, is something that we have to regulate well. Go in the middle here. Let's try to so I'll have to spend the week erasing. Blood pressure is something we do have to regulate consistently, more or less constantly, because you need pressure in order to push the blood through your circuits in order to perfuse your tissues. The whole point of having a circulatory system. There are a number of mechanisms to regulate blood pressure, both neural, which regulates blood pressure in the very short term. It involves, as we discussed in the video, the sympathetic nervous system, and endocrine, which will regulate blood pressure in the longer term. Okay. Regardless, we have evolved mechanisms mainly to raise our blood pressure. The big threat to your survival is low blood pressure. High blood pressure only becomes a threat in extreme conditions, which we really don't have a mechanism to handle, other than the normal neural mechanisms which will lower your blood pressure. Okay? So if you develop hypertension, for whatever reason, your body really doesn't have a good way of lowering that naturally. Okay? So you'll see we have a whole bunch of mechanisms for raising blood pressure, but only a single hormone system really to lower it, apart from the neural mechanisms, a single endocrine mechanism to lower it. Now before we discuss this, we have to consider a couple of things that are going to play into this. The blood pressure that's a proportional symbol, it's also an alpha, directly proportional to the volume. The higher the volume of the blood, the more its pressure. Okay? And also to the resistance. The higher the resistance, the higher the pressure. Now when I say higher the pressure, I mean in front, between the heart and wherever the resistance is generated. In our case, resistance is generated in small arteries called arterioles. So when those are constricted, the larger arteries that lead into them, the blood backs up into them and the pressure goes up. It's like if you put your thumb over the end of a garden hose, the pressure inside the garden hose goes up. You increase the resistance. Okay? So anything that raises resistance will raise blood pressure. Anything that raises volume will raise blood pressure. Anything that lowers resistance will lower blood pressure. Anything that lowers volume will lower blood pressure. Okay? And because of the complexity of the mechanisms to raise the blood pressure, I'm going to do those first, and then we'll do the single mechanism that lowers blood pressure. We'll do that separately. We may end up doing that next time. Okay. All right, so we're going to draw the blood pressure at the top here. Okay, and then we're going to look at what happens when this falls. All right. Now there's all sorts of reasons why your blood pressure would fall, right? You could have a hemorrhage, you could be bleeding out, but of course that's a rare traumatic condition. A normal way that your blood pressure might fall, one that you might have happen every day, is when your fluid in your body evaporates. So you lose it through your skin, you lose it when you exhale, right? So you lose volume goes down, pressure goes down. Now we can detect that directly, but there's another way we can detect that we're losing water to the environment. Because when we lose water to the environment, we don't lose salt. All the salt stays behind. So you lose water, you keep the salt, your osmolarity goes up. Right? So you have rising blood osmolarity. Now this is not a direct effect on pressure, but it's a consequence of losing that volume. So the first thing we're going to look at is what happens when the blood pressure falls due to rising osmolarity. This is detected in the hypothalamus. There are osmoreceptors here in the hypothalamus. And in response to that, they release a hormone called ADH, anti-diuretic hormone. Okay. You can see where it gets its name. Diuresis is loss of water in the urine, right? Increased urine volume. So anti-diuresis would preserve that volume in the blood. Okay. It's also called vasopressin because it raises blood pressure. And you know this one actually is produced via the posterior pituitary gland. Right? Remember we have those neurosecretory cells, those neurons, that send their axons down through the infundibulum to the posterior pituitary, and they release their neurotransmitters as hormones there. And in our case, that posterior pituitary produces two different hormones, oxytocin and ADH. They're very similar, they're both 9 amino acids, not long. Okay? Alright, so what does ADH do to raise blood pressure? Well, it has a few targets. First, blood vessels, increases vasoconstriction. You have an increase in vasoconstriction, and that raises resistance. Right? So resistance goes up, blood pressure goes up. It also targets sweat glands. We're going to have decreased sweating. And that will raise the volume because we lose less volume to sweat, to evaporation. And then the kidneys we're going to have the major effect of ADH, which is increased water reabsorption. That will raise the volume, but it will also lower the osmolarity. So here we had rising osmolarity, here we have falling osmolarity. There's your feedback pattern. Right, you reabsorb more water without reabsorbing salt. Okay? ADH allows you to reabsorb water from the filtrate. Remember, you filter everything out, it becomes filtrate, you reabsorb. ADH allows you to reabsorb filtrate without reabsorbing salt with it. So it's like dumping pure water back into your bloodstream. That raises the volume, but it also dilutes the salts so the osmolarity goes down. Now, whenever your blood pressure drops, you'll also see falling flow to all the organs, really. But this is going to be detected at the kidneys. The kidneys will detect that falling blood flow to them. And we'll see later on in the semester how they do that. Okay? In response to that falling blood flow, the kidneys release a substance called renin. R-E-N-I-N. Now, renin is not a hormone. It's not a hormone. It is an enzyme. And it will trigger a set of enzymatic reactions that will produce a hormone. Your liver, as you may remember, one of its jobs is to make proteins that end up in your blood. Most of it, the protein that it makes for your blood, is called albumin. And albumin is just there to raise the osmolarity of your plasma. It's called colloidal protein, or oncotic pressure. But there are a number of other proteins that your liver makes quite abundantly that circulate. Now, one of them is called angiotensinogen. And it comes from the liver. So that's circulating in the blood, angiotensinogen. You may have picked up that gen means it's going to make something called angiotensin. Angio means blood vessel, tensin means tension, pressure. renin catalyzes the conversion of angiotensinogen to angiotensin 1. Angiotensin 1 is still not the active hormone. But what you have done by releasing renin into the bloodstream is turn the entire bloodstream into an angiotensin 1 factory. Renin circulates around, it encounters numerous molecules of angiotensinogen, which have been produced by the liver this whole time and are normally circulating. So you put this enzyme in and it starts converting all that, or a lot of it, to angiotensin 1. As that blood flows through the body, it then goes into the heart, and the next place it goes is into the lungs to be oxygenated. And in the lungs, there is another enzyme called ACE, angiotensin converting enzyme. And ACE converts angiotensin 1 to angiotensin 2. The Revenge of Angiotensin. So I feel like it's a sequel, so I have to give it a silly sometime. No, but this is finally the active hormone. Okay? So we talked about this last time when we introduced the endocrine system. That one way to regulate hormones is producing them in inactive forms, which we call prohormones. Right? Well, this one has 2 steps. So this is your prohormone, angiotensin 1. Angiotensinogen is your pre-prohormone. Right? So first you have to make the prohormone, and then you can make the hormone. Want to go to this trouble? We'll go ahead producing that precursor. Again, as I said, turns the entire bloodstream into a factory to make this quickly, so that angiotensin 2 levels can rise very quickly, even with a little bit of renin produced by the kidneys. All right, now angiotensin 2 has a number of effects. Okay, it's going to go to the kidneys. In the kidneys, it's going to increase vasoconstriction. Okay, now, of course, as we saw up here, increasing vasoconstriction increases resistance, which raises pressure. Okay? But that was when we were doing it generally. ADH has general effects throughout the body on vasoconstriction. Angiotensin 2 mainly causes vasoconstriction in the kidneys. Now that does raise resistance, but that's not the main effect, right? By raising vasoconstriction in the kidneys, we reduce filtration. And if we reduce filtration, we have a lower urine volume, which raises the blood volume. Right? So we've reduced the amount of blood flowing into the kidneys by constricting their blood vessels. Therefore, we've reduced the amount of filtrate we're producing. That reduces the amount of water we're losing as urine, so our blood volume is raised. Angiotensin 2 also affects the hypothalamus, where it increases the sensation of thirst, which of course will raise the volume, assuming you have something to drink. Angiotensin 2 is a very potent stimulator of thirst. All right. Another place angiotensin II is going to have an effect. Make myself some more room over here. Okay. Is it's going to go to the adrenal cortex. Specifically, it's going to affect the zona glomerulosa. You recall from last week that is the most superficial of the layers of the adrenal cortex. It's the thinnest, and it produces mineral corticoids, which are hormones, steroids that regulate blood mineral levels like sodium and potassium. Specifically, we're going to get the release of aldosterone. Aldosterone is produced by the adrenal cortex, the zona glomerulosa. Aldosterone then goes back to the kidneys, where it increases the reabsorption of water, but also sodium and chloride. And of course, that will raise the volume. Okay, so we got a rather complicated thing going on here. Angiotensin II stimulates the adrenal cortex, specifically the zona glomerulosa, to produce this hormone aldosterone. Aldosterone goes back to the kidneys, where it increases the reabsorption of water, but also sodium chloride. So here we have a hormone where we reabsorb water and salt together. We raise volume, but without lowering osmolarity. With ADH, we reabsorbed water alone. So our volume went up, but our osmolarity went down. Here we're reabsorbing water and salt together, so we are raising volume without lowering osmolarity. Having these two hormones, ADH and aldosterone, work together allows us to somewhat independently regulate blood volume, blood osmolarity, and specific minerals like sodium and potassium. All right, we're going to see this again and again and again. By the end of the semester, you're going to be so sick of hearing about ADH and angiotensin II and aldosterone. Right? But they kind of permeate all these systems that we're talking about. Okay, now there's one more thing that happens when the blood flow to the kidneys is reduced. The kidneys can detect the reduction in flow rate specifically, right? And again, we'll talk about how that happens in the semester. But they also, when the flow goes down, oxygen also goes down. Now let me redraw that. When the flow goes down, we also get falling oxygen to the kidneys. And when the kidneys detect that falling oxygen, they produce a hormone called erythropoietin. Never spell that right. Erythropoietin. Poiesis refers to cell production. Erythropoiesis refers to the production of erythrocytes, which is another name for red blood cells. Okay? The entire process of making blood cells is called hemopoiesis, right? Making blood. This, of course, goes to the bone marrow. Where we see an increase in the production of red blood cells. That raises volume. In a typical sample of blood, about 45% of the volume of the blood is red blood cells. So if you add more red blood cells, you can have a significant effect on volume. Raise the volume, or raise the pressure. Something else happens here that I didn't mention. We also increase the viscosity of the blood. You know what viscosity is? The thickness, how easily it flows. You add more of these solids, the viscosity goes up, and that raises resistance. Okay, I don't know if that's a super significant effect, but it's there. Right. Now there's one more thing that happens here. Angiotensin 2, as we've said, it causes reduction in urine production in the kidneys. It stimulates thirst in the hypothalamus. It stimulates the adrenal cortex to release aldosterone, which causes us to reabsorb more water and salt. But also, this is a minor effect, but it's there. It also stimulates the release of ADH. Now, before we move on, we have 10 minutes left, so we've got time to cover what happens when blood pressure goes up, because it's not much. All right. But there's one thing I missed over here. If you still have your blood glucose chart, one small thing to add to it. There's another hormone that's produced by the beta cells called amylin. What amylin does is it reduces stomach emptying. Okay? Now, why does that make sense? Amylin reduces stomach emptying. Well, the glucose is too high. Where did that glucose come from? It was absorbed in your small intestine. Where did that material to be absorbed come from? It came from your stomach. So basically what the beta cells are saying is, slow down stomach, give me time to process this glucose, and then I'll let up on the amylin, and then you can empty some more, and then we'll have some more stuff to absorb, right? So it's slowing down the process of emptying the stomach, so you have time to process the glucose that you have. And, you know, cool thing to have there. All right, so I'll do elevated blood pressure over here. And again, there's not a whole lot to do. Okay, so we'll put the normal blood pressure. Well, first of all, let's kind of complete the loop here. All of this stuff raises blood pressure. Then we'll put the normal blood pressure line down here. So now we're looking at the upper side of that. Okay. What happens when blood pressure goes up? don't have a whole lot of mechanisms to deal with it in the long term, right? We have neural mechanisms that can deal with short-term elevated blood pressure. We don't have many endocrine mechanisms to deal with it long term. This is detected in the atria of the heart. When you have increased blood pressure, you have more blood flowing back. That's increased venous return. That increased venous return, which means there's more blood flowing back into the heart. The first chamber that the blood goes into is the atria. And so you see the walls of the atria stretch. Okay? And those walls then release atrial natriuretic peptide. Atrial, from the atrium. Peptide, it's a short protein. Natriuretic. Natri refers to sodium, uresis refers to in the urine. It's a hormone that results in more sodium in the urine. But also, of course, more water as well. Now, what does atrial natriuretic peptide do? It basically acts as an antagonistic hormone to decrease the effects of epinephrine this is effects. It doesn't actually decrease the amount of those hormones, it blocks their effects. Decrease the effects of epinephrine, norepinephrine, ADH, okay, and also aldosterone. Okay? So basically, we've got something here that just turns around and blocks all those. Not completely, but reducing their effect. So that's going to result, of course, in lowered volume and lowered resistance. I usually draw this one an S because there's more than one type. That's a detail. Okay? Atrial natriuretic peptide reduces the effects of epinephrine, norepinephrine, ADH, aldosterone, so forth. Okay? And why do epinephrine, norepinephrine matter? Well, those are the ones that mediate the neural responses to blood pressure, right? As we discussed in the video. We'll see that again when we talk about the stress response. Okay? There's one more thing it does. It's a direct effect on the kidneys. It has a direct effect on the kidneys. It increases filtration. Which relate to increased urine and lowered volume. Okay? And all those things, of course, lower the blood pressure. Where does it get its name? Well, remember, aldosterone increases the reabsorption of sodium. So if you block the effects of aldosterone, you'll have more sodium in the urine. That's where its name gets its name. All right? So that is blood pressure, the endocrine regulation of blood pressure. We'll see more about the neural regulation, right? We saw that last night. We'll see more about it when we talk about the stress response.